Cool. Hello, everybody. Thank you for coming. Thank you for waiting through this entire day for this session, obviously, because this is going to be it, hopefully. The talk is about Rust and Haskell, and this is a little bit of like a comparison talk, even though the languages are sort of different. But I thought, like, from the way that I came into both of these languages, I hope it makes sense, and I kind of wanted to share my view on things, and then the things that I thought were interesting when learning these. So a little bit about me. Hi, I'm Lisa. I'm a Berlin-based web developer. I work at a nonprofit during the day, and in my free time I do a lot of video games at game jams. I also try to be a digital artist, whatever that means, and I would consider myself a functional programming enthusiast. So I come from a very dynamically typed web-focused background, so JavaScript, Ruby is still what I use at work most of the time. I was introduced to the functional programming world through Clojure and ClojureScript, which are also dynamically typed. So this was kind of easy for me to get into, and I also really like the lispiness of things. And in my journey of apparently learning a new programming language every year, I started learning Rust roughly 1.5 years ago, and this was my first encounter with static typing, and also a low-level systems language, which I hadn't worked with before. So this was kind of interesting, and this is sort of this nice journey where I oh, Rust is so cool. There's all these weird things that I don't know of, and then since it was the first statically typed language for me, it was this is so cool, and you have types, and you can do the stuff, and I wondered are all statically typed languages like this? And I know some people who come from C# and they're no. And I was okay, so where all of the things that I like about Rust, where do they come from? Because Rust is relatively young, only a couple of years old, and which gave Rust the advantage of having learned a lot of things from all the languages that came before it, and then also applied to this low-level system thinking. And this is kind of start the sentence again, where I was trying to think of it was possible for the Rust people to bring all these cool ideas and concepts to this low-level language, and I want to find out where are they coming from. So about a month ago, I started learning Haskell because people told me you should look into Haskell if you're interested in where all these things come from. So I was oh, Haskell, that's weird. That's so very functional, and I know some functional stuff. And if you look at the Rust website, so this is just rustlang.org. You have the obvious sales pitch of it's a systems programming language. It's super fast. It's memory safe. For it comes from certain other kinds of features that it has. So it's okay. It doesn't really actually mention functional programming at all. But then thought, oh, there's this little featuring list, and it has things okay, there's type inference, okay, pattern matching, okay, something that they call trait-based generics, might be interesting, and then at the top, something this weird combination of words called zero-cost abstractions. I'm okay, now that I know what all these things mean, it's okay. If we just look at these four features that they advertise at the website, can we make some of a functional programming talk out of it? So can I sell you on this? And I think I can, hopefully. So now I have the problem that my emojis are not showing on the slides. So this is the thinking emojis. I think this could be a very good functional programming talk. And I just want to get started because time is limited and we don't have a lot of it. Let's start with type inference. So this is going to be a very basic introduction to the whole type inference thing. Because if you come from Haskell, you're type inference, I know about type inference. Let's look at a super simple example of we define a function, double me, which takes x and then multiplies x by 2. And then when we call it with 8, we get 16. And this just works, and we didn't even have to annotate types because type inference. So this is very cool. This is something that makes it, for me, as a person coming from dynamic type languages, very easy to just get started. And the other cool thing is that if I try to then call this function with strings or an empty list or something, we get an error. So the compiler, in this case, has us covered. So this is cool. And this also like works on lists. And I'm just gonna like run through this. So if we have a function that, for example, takes the first element of a list and multiplies that by 2, we can call it with a list of numbers, and then it does what we tell it to do without inferring type, without having to annotate type explicitly. And in this case, if we also like would do this with a list of strings, we would get an error, because Haskell says like, hey, you pass in a list, but like you're multiplying by 2 anyway, so it has to be something with numbers, right? So we don't have to annotate type in these cases, but it's still nice if we do, so to make it more readable for other programmers, for the humans. And this is kind of nice. So we could say like double me could be like, we take an int and we give an int back, and double first of list takes a list of int and then gives an int back. And this is nice. It's like you kind of sort of know what's going on. And this is actually enough to know, like all the things that we need to know to like look at the Rust equivalent of this. Rust also has type inference. It works a little bit different. Rust tries to infer types whenever possible. There's like certain cases when it can't do that, and then it will tell you, or like the compiler will give you a message of like, hey, I'm not really sure what this type is supposed to be. Please help. Let's look at an example. We have a main function. Maybe as a side comment, so I tried all the examples in Haskell in just the REPL, and this works, but there is no like real REPL in Rust at the moment. So I tried to like have all the code examples in Rust in a way that you can copy paste them and run them yourself, which is why I have all like the extra stuff, and like there's always like the main function, so you know where to put it, in case you want to like do this at home. Okay, so we have a main function. We could assign a variable that we call elem and like assign it 5. And then we could say, okay, like double elem is like elem times 2. And then we print this and we get 10. And then no types were annotated. And Rust is like, yeah, something with numbers, multiplication works. And we have the same with lists, or in this case, I'm choosing a vector because it's more flexible with like dealing with lists of things. So we create a vector of numbers, and then we say, okay, so like double the first element of the vector, and we like use bracket notation here to get like the 0 index element and multiply that by 2 and print that out, and then we get 4, easy. And now you might be wondering why I used like variable assignment instead of like making it a function, which is kind of like the point of functional programming. And this is where I wanted to talk about special cases of functions in Rust. So in Rust, you always have to annotate types in functions, like for all the values that you put in and like all the values that are returned. And this has something to do with the way that Rust calculates, or like has something to do with like the broader scope of like memory management and borrowing in Rust, which are concepts that I will not talk about here because there are a lot of talks on this, but I don't want to give this talk. So this is like sort of like the main reason why we need type annotations on functions, so that Rust has like these checkpoints to say like, hey, this type is needed here, so I can check against that. Okay, so how would this look like? If we take the double first of vec and like put it into like a proper function, this would be the syntax for it. We have fn as the function keyword, then like the name of the function, and then we say, okay, we get a parameter v, which is of type vector of an unsigned 32-bit integer. There's a lot of different integer types and float types in Rust because of this like low levelness, but don't worry too much about it. So u32 and i32 are unsigned and signed integers. And in this case, we have a little error and then say, okay, we get an unsigned 32-bit integer back. And then in curlies, we get the function body, which just does what I had before in the example. Then in the main function, we can like create a vector and call the function on the vector and get 4. Simple. This was just like the beginning of sort of like introducing you to like some Rust syntax, and I'm like where type inference is happening, but also like is different a little bit. And we need this for like the next. So this is kind of like building up. on the next topic of trait-based generics, because we're like going to talk about types a bit more. So, trait-based generics. What is this? First, what are generics in Rust? So they are abstract stand-ins for a concrete type. So this may seem familiar if you look at it. If we define a function first and last that, for example, takes a list and or like takes a vector and returns a vector of the first element and the last element in the list, because I need an example function. We can say it's like fn is like function keyword first and last, and then in angle brackets we get t, which is the generic type. And this could be any variable, like, or any name could stand here, but like convention says like, okay, t for our generic type here. And then we say we get a vector, and this is the vector of this generic type t, and we get, return a vector of generic type t. And then we can say it's like, okay, create a new vector with the first and the last. There's a little bit more verbose stuff going on, but don't worry too much about it. We'll partially cover it later. Right, and this then works with vectors of numbers, or with vectors of floats, or with vectors of strings, and so on and so on. Boom. So if you're coming from like a Haskell background, you might say it's like, oh, type variables, maybe. And then yes, the counterpart in Haskell would be type variables. So let's also define a first and last function that takes a list of something, and then like returns a list of like the first and last element in that list. So we might say like, okay, it's a list of A, and we return a list of A, and then it might look like this, maybe. It's just way shorter and looks much nicer, but it basically does the same thing. So I could use this for calling it on a list of numbers or a list of strings or whatever. So this is kind of nice, I thought. So this is kind of like the generics thing. They're pretty similar in my opinion. There's also traits in the trait-based generics term. So traits define behavior that types can implement. So this is also known as interfaces in other languages. Maybe let's go with an example of the display trait in Rust. So display is a trait that defines the string representation of a type for user-facing output. So if you like want to print something to standard out, the display trait is indirectly called to format this. And we can look at the Rust documentation online and see it's like, okay, trait comes from the standard library. It's part of like the formatter module namespace thing. And we have an example of like how would we go and implement this on our own type. And I'm just going to like actually take this example and run you through it. We have our own data type. With the struct keyword, we define our own type called point in this case. We're going to give it an x and a y. It could be a coordinate or something. And then we implement the display trait for this point, and then we define the function fmt format, which we know that we need to implement this from the documentation. And which there's a lot of like type annotation going on, but in the end we return a result, which is kind of like either the result that we hope for or an error. And then we like use the write macro to like build up the string of the string representation of our type, which in this case is just a string of x and y in parentheses. So if we like then create a point, print this, it would print out point in this like parentheses, comma separated notation. So this wasn't too bad, but you might be like, well, this is like type classes somehow, and it's like, yes, in Haskell this is basically type classes. The equivalent of the display trait is the show type class. So if we were to do the same thing in Haskell, define like a point that has an x and a y, and we could derive show from it. So like just take the same time class and say it's like, hey, show is also like something that could happen on point. I could like say, okay, so then like point is 2, 3, and then I could say show point, and then we get this like super nice string representation of it. Another way to do it is I can implement a function that takes a point and returns a string. I could call this display. and then just have my custom string, and then say, okay, display point, and then we get this nice string output. So it's a little bit of like different ways of like looking at things, but to me it was like, oh, that's interesting because they're coming from Rust and like looking at the Haskell like equivalents or like the counterparts. It's sort of like, oh yeah, I can see some like where all the stuff comes from. And this also like traits and generics together give us nice things like trait bounds. So if you, for example, want to like define a function that is called shoutout and then gives us, or like returns a string of whatever, like just adds a bunch of like exclamation marks because we shout out loud. We could write it like this. So we take a generic type T that implements display, so like something that we can, like that has some sort of like string representation on it, and then just like output a string with all the exclamation marks. And in Haskell, we would call this class constraints, where the shoutout function would like take an A that implements show, and then we just like give back a string that is like this whatever we get into with a bunch of exclamation marks. So I'm like, yeah, and ooh. So with traits and generics and trait bounds and stuff, we have like sort of built up the foundation for one of the coolest features, I think, which is pattern matching. And once again, it's like, yes, pattern matching. Definitely a thing in Haskell. Let's look at a simple example where we define a shape, and shape can either be a circle that takes floats, like three float numbers, whatever, or a rectangle of 4 floats, and then we can define a surface function that takes a shape and then returns the surface area as a float. And then we can say, okay, surface, if we match it on a circle, we're only interested in the last argument, which we take then as the radius, and then calculate the surface of the circle. Or we can say, hey, if it's a rectangle, we're going to use the floats as like the upper left point and the lower right, and then calculate the surface area of the rectangle based on this. So that's pretty cool. And then if we call a surface with like a circle of 10, 10, 10, so like 10 would be then the radius that we use, and then we get this back. I'm not going to read the number. And this is like astonishingly similar if we look at this example in Rust, where I define an enum shape, so like shape can either be a circle or a rectangle. I define them as tuple structs, so they just hold like a couple of values within them. And then the implementation of the surface function would then look like this, like a surface takes a shape, returns a float, and then we match on the shape and say it's like, hey, if it's a circle, you're going to ignore the first 2 arguments and just use the third one as radius, calculate the surface on this. And if it's a rectangle, we're just going to use the X and Y values for like the points opposite of each other and calculate the surface area on this. And then in our main function, for example, we could call it like this and also get the same result. So this is kind of like, I was kind of very surprised to see this, like the similarity in the pattern matching. It's just like, wow, mind blown. Because I think it's really cool. Which brings us to, the last point, which is a little bit more kind of trying to tie things together, hopefully, which is this like super cool buzzword of zero-cost abstractions, which I think is sort of like kind of used in sales pitches for us, because it's like, yeah, zero-cost abstractions, and I'm like, what is it? What do you mean by this? I mean, free stuff is cool, but is it like really free if it's zero cost? And what like the definition that I would rather use is, like in Rust we get to use higher level concepts at no additional performance cost. Which also might seem like a very abstract definition. But I want to like kind of like show this by an example, and by talking about higher order functions. They're pretty standard concept in functional programming. But just to like recap, let's look at it in Haskell as a like introductory example. So map, for example, is a higher order function. It takes a function as an argument. So we could do like a simple thing like this. So map takes +3 as an input, and then like we apply it on every element in the list, and then we get another list out where +3 has been applied to every number in the list, for example. And the other one is filter, where filter takes a predicate, so like a function that either returns true or false, applies it to every element in the list, and then only returns a list with only the elements that for which the predicate is yielded true. So this would be the filter function. So this is a very simple example. So let's look at this in Rust, because this is really interesting. If you remember when when I talked about functions in the beginning, I said that functions you always have to annotate type, always. And this is kind of like, here's like a more verbose explanation of this, because this has some consequences in the follow-up. So in Rust, function declarations are treated as statements, whereas function calls are expressions. And this has some like, I'm missing the word. Different sentence. Which means that statements, it means that statements cannot be evaluated. So they cannot, they cannot be evaluated, and they don't have like a representation as a value. And that also means that we cannot assign them to variables, and we cannot use them as a replacement for any other value. Whereas expressions can be. So I could not define a function and like pass it to something, but I could call a function that then yields a result and could pass that to something. So this is a little bit also weird, there's more. The moment we define a function with its name, this name becomes part of the type of the function. So that would mean that even if we define two functions with the same type signature, but they have different, they then have different names and therefore different types. So I couldn't specifically say, hey, this function could take another function of this type, because when we define a function, we have to annotate type. So this is kind of like not working if we want to like then do something like creating functions on the fly or dynamically. Exactly. Because we can't really know what type a certain function will have in advance, and then we would need to like specifically annotate this. I'm writing here, it's not easily possible, because apparently you can if you want to like point pointers in memory specifically to certain things, but I don't know how to do this, and I would not recommend it, unless you really know what you're doing, I guess. So if you just listen to this and you're like, wait, are you trying to say there are actually no higher order functions in Rust? Well, not in the way you might be thinking of it like this. So it's not like part of like, okay, I can define a function and then like pass this function in. But there is a way around, because the Rust people were like, we can't have like a new systems level programming language that is basically just like C without any cool stuff. So we need to need to build something that can like give people this like higher order power that we're like actually now used to in a lot of other languages. So what they built in Rust is called closures, which is an unfortunate name, I think. So closures are anonymous functions that can capture their environment. So yes, sort of closures, but closures are also anonymous things. So closures with closures, I guess. And these like closures in Rust fill all the gaps that like functions can't cover because of like their annotating type. The annotating type kind of behavior. So we can store the declarations in variables and then like pass these variables around and also like reuse them. This is really cool. We explicitly do not have to annotate type on closures. We can, this is optional, but we don't have to. This gives us more freedom and like also the ability to like be more dynamic about like the way we put functions together. And the way this is done is that the Rust compiler will then, when it infers types on compilation, just like infer the type on like whatever is used first within a closure. So if you reuse a closure and then on the first time you use it with integers, this is like, okay, I'll let this go, or like let this pass. And if you then on the second time use it with strings, for example, the compiler would just say like, no, first time you said like this closure will be used with an integer, and now you're using it with the string, and then this cannot work. So this is cool. So if we like pay attention to this, we can make this work. And the other thing is that closures are always implement one of three traits, the fn, fn mut, or fn once trait. And this is kind of handy because then we can, when we have to annotate function types, and we know that we will pass in a closure, we can use trait bounds and say, okay, this is going to be like a generic T, but it's going to implement fn, so it will be a closure, but we don't have to be explicit about what will exactly be going on later on. So this is cool. And now I have like a little example of like using closures with iterators, because I'm going to want to come back to like the map and filter examples. So iterator, the iterator trait is like a very popular trait in Rust. It deals with doing things in a sequence or on a sequence. And this is where all the cool functions that we know as higher order functions usually are implemented with. So let's, for example, create another vector, just like 15316, for example. Then we call into iter, which is then like converting just the vector into this iterable thing, which then like, so this is where the iterator trait comes into effect. And like on the iterator, we can, for example, call map. And here you see the closure that we pass into map, which is this like pipe-like syntax that is like maybe like looks familiar from Ruby, if you come from Ruby. And we say, okay, so for every x, apply like add 3 to x, and then we call collect. What is collect? This comes from the fact that iterators are lazy, so you can like do all sorts of stuff with iterators. But in this case, we just want to call map, and then we want to say, okay, run through the sequence, like iterate through the sequence, and then like give me the result. And this is what collect does. And similarly, filter would also take a list, would also take a vector, and then we could call into iter, call filter on it, pass in the closure, also call collect, and if we then print out the results, we get the same thing as we did with Haskell. And coming back to the zero-cost abstractions thing is that why we can, like I could have also like written these examples instead of like map and filter with a for loop and like checking these with like if something and then like doing this like a very imperative style. There is the possibility and like explicitly the want from the Rust implementers to like use more higher level concepts. But at the same time, there is no performance penalty for this. So like using a map or a filter or just like chaining these together will run just as fast as if you manually code a for loop. And it's just like so much nicer to read and like so much nicer to think about this and like think about your program in that way. So I think this is really cool. And there's like a bunch of other like nice things like this in Rust where you think like somebody who's really into functional programming wanted this feature in the language, and they did like, and they did have success with it, which is cool. Okay, that was all a lot, and like run through. I hope the examples were like basic enough so that it was like easy to follow along. But yeah, it was a lot, and there's a lot of features in Rust that you could like. People give a lot of talks about, but I wanted to specifically focus on these like little things and bits that that I thought were like where Haskell was definitely like an influence on Rust as a language, and I thought it was kind of funny from the talk yesterday where what Haskell taught us when we weren't looking. I was like sitting in the talk, it's like, wow, my talk is basically an implementation of this theory. So that was kind of like, yeah, I think that's true. Sort of like wrapping up, maybe Rust is definitely not a functional language, and I hope that you kind of saw that. It's just like it's an imperative language, but it has some sort of like yeah, it has multi-paradigm-ish support. So like you can do functional things. It is also at parts very object-oriented. But there's definitely influence from like the Haskell community and other more like functional languages and like concepts. And this is really cool because one of the cool things is that Rust is a very new language and with a very open community is that a lot of people like try to get more of these features into the language, and it works. I mentioned that there's no Rust REPL. There's one kind of old-ish implementation by like a community member, but there's also an official RFC where people started commenting again a couple of months ago. So maybe we'll have a Rust REPL, which I think would be like super duper cool. So if you want to like click on the link and then like emoji upvote the thing on GitHub, yes. Also, I had this like super fun conversation on Signal a couple of months ago where Jose, who's not here, was like, yeah, you should talk about higher kind of types because functional folk love that. And it's apparently possible in Rust. It was first called associated type constructors, but the RFC that was merged in August is called generic associated types. So shout out to Daniel in the other room who will say something about higher kind of types in Rust. I know that, but I'm not there to like, woo, in the audience. Okay, so all these things. I have one more slide with like, the title of the talk was Rust and Haskell sitting in a tree and there are no trees. And this is like maybe for all like aspiring speakers, think about the title you give your talk, especially if your talk is not written by the time you send in the abstract. It's not a good idea, so there are no trees, I'm sorry. But this is it. Ask me any questions, maybe resources. I mainly learned Rust by reading the Rust programming language book, which is available for free on the Rust website. There's Rust by example, which is a very nice and detailed guide with code examples that run in the browser to like just like go through the concepts, especially the ones that I only hinted at, like the lifetime borrowing thing. And I also I learned Haskell with Learn Your Haskell, which is a very good book for like, that makes no assumptions and which is really nice if you like just want to like learn a thing or two. Thank you.